Hello everyone, and it's been a long time I have been here, and there were a few changes in between, and because of that, I could not make my videos. Now I'm back again, and this time I'm going to have monthly themes for videos. All right, monthly themes in the sense that are going to be different topics for different months. So the theme for this month is motion and forces. So mostly we are going to be talking about kinematics and forces this month. And yeah, in this particular video, I have come here to solve IB past paper questions. Now, you might be thinking why I'm stressing more on questions this time. Rather doing the concepts, I'm going to stress more on questions this time. And it's very much important because I want to develop the correct thought process in your mind. I'm going to show you something that is very much essential to do physics, and that's having a right thought process in your mind. Okay, right? So, without wasting our time, let us get into the first question. I hope, and if there are some IBDP students sitting here, yes, this video is for you. So let me screen share my screen. As you can see that this is my first question, and it's from year 2012. But a very good question. Abe and Ewan are sitting on opposite sides of a merry-go-round, which is rotating at a constant speed about a fixed center. The diagram is shown below. So as you can see, the upper shot of two students or two children sitting on a merry-go-round, and you can see that they are diametrically opposite. Can you see? First, you need to imagine what you're looking into. You can see here that they are diametrically opposite, right? And they are going in a merry-go-round, and the speed of the rotation is constant. Where is it written? It's clearly written here that the speed of rotation that you are having is a constant. Okay, it's a constant speed of rotation. I have a constant speed of rotation here. Okay, now Abe is moving at 1 meter per second relative to the ground. Right now, Abe is moving at 1 meter per second, so his speed is this side is 1 meter per second, students, relative to the ground. That means if someone was standing at the ground here, he would be seeing Abe moving with 1 meter per second. So can I say even Ion is moving with 1 meter per second? Right? They both are the part of the same merry-go-round, and you know that merry-go-round in the diameters. If both are sitting in the diameters, both the end is going the same speed but in opposite direction. In opposite direction, right? So if Abe is moving with a speed of 1 meter per second with respect to ground, again, I don't know how you pronounce it, Eon also is going with the speed of 1 meter per second with respect to the ground. Okay. Now, the first question asks you determine this magnitude of velocity of Abe relative to Eon. So, first thing, so there are two possible answers here, and you should know why two possible answers exist in this case. First, if you are sitting, let's say that you are Abe and you're looking at Eon, you will basically see Eon just sitting in front of you without moving. So relative to Abe, Eon is not moving because he's exactly opposite, right? So think in terms of Abe, okay? And you're looking at Eon, or think in terms of Eon, and look, you're looking at Abe. So technically, Abe is just sitting still in front of him. So the relative velocity of Abe with respect to Eon is actually zero. I would say the relative speed is zero. But there is another way of looking into it. Now, Abe moves 1 meter per second in, I would say this is my left direction, and Eon is moving 1 meter per second in right direction. Now, according to the formula of relative speed, when two objects are having speed in opposite direction, you need to add them. So the relative speed of these two guys are going to be VA, Abe speed, and Eon speed, VE. So technically it's going to be 1 plus 1, 2 meter per second. So the relative velocity according to your this relative velocity according to I would call the vector form. it's going to be in opposite direction. The relative velocity according to vector form is going to be in opposite direction. But when you are actually sitting in front of him, its velocity is zero. Relative velocity is zero because you are not looking the other person in motion. The person is still at rest. Okay. Now, second, the magnitude of velocity of A with respect to center of merry-go-round. Let us say that you are sitting at the center of merry-go-round. Let's say that there is a person, because we have to understand with respect to that point. Now, let's say that there's a person sitting at the merry-go-round and looking at Eon. You will actually find that Eon is not moving, right? From the center of the merry-go-round, you look at Eon, you'll find it's not moving because you yourself are being rotating along with Eon and Abe. So here also the relative velocity is going to be zero in this case. Here also the relative velocity is going to zero in this particular case. All right. Now let's go forward. Let's go forward and try to understand the other part. Now, as you can see here, the next part outline why Abe is accelerating, why though she's moving in a constant speed. So, guys, understand here one thing that they are going in a circular motion. They are going in a circular motion. So, once they are going in a circular motion, they are constantly being accelerated. What type of acceleration? See, here it says constant speed. It is the tangential speed that is constant, but they are changing direction, and because of that, because of that, they are going to have centripetal acceleration. Okay, and here, so I can say yes, they are accelerating best because there is a presence of centripetal acceleration as they are going in a circular motion. So you should be knowing about it, which is basically mv square by r is their centripetal acceleration. Part 2. Draw an arrow on the diagram, page 22, to show the direction in which Abe is accelerating. Now, the direction in which Abe is accelerating, since it's a centripetal acceleration, I would say it is accelerating towards the center. The direction of acceleration, students, is towards the center here. Right? Now, identify the force that is causing Abe to move in a circle. Right? Now, remember, when any object is going in a circular motion, the answer is very direct. When any object is going in a circular motion, it has a centripetal acceleration. And because of that centripetal acceleration, there is going to be centripetal force. There's going to be centripetal force. Centripetal force. And how am I going to get that? You know that according to Newton's formula, force is equal to mass into acceleration. Acceleration is already given here, and so just multiplied that. Sorry, the acceleration is not I have just written mv square, so basically I wrote a force acceleration value, my bad. So actually the acceleration value is v square by r. V square by r, the acceleration value is v square by r. So when you multiply mass to it, you are going to get mv square by r, and that's the force which is keeping a circle. So remember that it is the centripetal force that keeps an object in a circular motion. So here it specifically asks that a force which causes Abe to move in a circle, and that's the centripetal force. Now the diagram shows the side view of Abe and Eon on the merry-go-round. Now, till now we were looking at the top view of these guys going in the merry-go-round, but now you are looking at the side view of these people going in a merry-go-round. Now there's a question. Explain why Abe feels as if her upper body is being thrown outward away from the center of merry-go-round. Now understand, students, you know, as they are going in a circular motion, the centripetal acceleration is acting towards the center. But you should also know, according to Newton's third law, there is a force, there is a pseudo force which is acting in the opposite direction to centripetal acceleration, and I call it as centrifugal force. I call it as centrifugal force. So centrifugal force is a force which is acting in the opposite direction to the centripetal force. Okay, opposite direction to the centripetal force. So you can look here, it is in this direction. Centrifugal force is in this direction. Centripetal force in the opposite direction. Centrifugal is the opposite. I mean, centripetal is towards the center, and centrifugal is the opposite. Now, because of the centrifugal force, understand, because of the centrifugal force, the upper body feels to be thrown outward. The upper body feels to be thrown outward. Why? Because the bottom part of the body is attached to the, look here, the bottom part of the body is attached to the merry-go-round. The bottom part of the body is attached to the merry-go-round, and the upper part of the body is free, basically left free. So what happens because of that? It appears as if the upper part is trying to move away, right? Because of centrifugal force, it is kind of going outwards. Okay. Then we have Ion drags the foot along the ground to act as a brake. The merry-go-round comes in a stop after 4 rotations. Now remember, he has put his leg to stop the merry-go-round, but the merry-go-round stops only after 4 rotations. The radius of merry-go-round is 1.5 meter. Okay. The average frictional force between his foot and the ground is 45 Newton. Calculate the work done. Now look here. I have a merry-go-round and he puts his leg here. Let's say that he's putting his leg exactly on the radius. And he goes 4 times. He takes 4 rotations. So he goes 4 rotations, and that is when it comes to a stop. He goes 4 rotations. So they are asking you what is the work done. So I have a formula for work done which says that work done is force into displacement. Work done is force into displacement. Force, as you can see, is already given to me as 49 Newton, which is a frictional force. So see, when he is keeping his leg on the ground, there's a friction force that is coming. The force is frictional force. Okay, the force is frictional force, and he's taking now you need a distance. So how much of distance has the friction gone through for 4 rotation? And for that I need to find, I would say, the circumference of the merry-go-round. So 4 times it has gone, circumference of the merry-go-round. So basically 2 pi r. I'm having 2 pi r, right? So 2 pi r. So it's going to be, the radius is already given to you, 1.5. Okay. So the distance that has traveled here is 4 into 2 into 3.14 into 1.5. Okay, 3.14 into 1.5. 3.14 into 1.5. So you would see here the distance. If you do the calculation, here accordingly, your distance you will be getting somewhere around 37.7 meter, right? You'll get somewhere around 37.7 meter. Okay, and that's your distance. Now you have to substitute the value here, 45 into 37.7 meter, 45 into 37.7 meter, and when you multiply it, you are going to approximately get in 1700 joules. Now students, this is the work done. Okay, this is the total work done in going around like this. Okay, this is the total work done in going around in a circular motion, guys. Okay, all right, so there is a continuation. It's a pretty big question, students. It's a pretty big question, and yeah, that's why you're able to see this, so many things in here. Okay, so now the question says A moves so that, okay, that he's sitting at the distance of 0.75 meter from the center of merry-go-round. So what Abe does now, the Abe is not sitting at the radius. The Abe is not sitting at the end. Rather, Abe moved little closer. Abe has moved little closer to the center, basically. Okay, now Eon pushes the merry-go-round so that he gets moving at 1 meter per second. So now remember, Eon has actually stopped, right? Eon has basically stopped the merry-go-round. He again applies the force and starts going around. So now Eon has started, and now Eon is moving with the speed of 1 meter per second. Eon is moving with the speed of 1 meter per second. Okay. Now the question says, determine ape speed relative to the ground. Determine ape speed relative to the ground. Now the radius has changed, right? My radius has changed. So I'm going to have a new radius. So I have a formula here. Okay. Now in this, you should know that we have a formula which is v velocity is 2 pi r divided by the time period. Velocity is 2 pi r divided by time period. Okay. So actually they're asking the speed of revolution here. The speed of revolution. Now what are the changes that is going to happen here? You would know that there are few changes happening. My R value has changed, right? My R value has changed. Okay. Now, if you see the formula, your velocity is actually proportional to radius, keeping the other things constant. Students, look here, I'm not changing anything else. I'm not changing 2, I'm not changing pi, I'm not changing t. So keep this all thing as constant. So you would observe that velocity is directly proportional to the radius. Okay. Now the radius becomes half. Initially the radius was 1.5. Now the radius became half. So speed also becomes half, students. Okay. So the speed is 1.0 meter per second. Now this was when the radius was 1.5. When it was 1.5 meter, the radius was 1.5 meter, my speed was 1 meter per second. So when now it's 0.75 meter, my radius, students, is, sorry, not my radius, my speed is, students, 0.5 meter per second. So this is the relationship that you should know for a circular motion. Okay. Now they're asking calculate the magnitude of ape's acceleration. So you know ape's velocity has changed. The formula of acceleration is the formula of acceleration is v squared by r. Now you are putting the new v value, right? You are putting the new v value, that is 0.5, and your r, and you are putting your new r value. You are putting the new r value also. You see, 0.5 whole square divided by 0.75. Students, you will find that you will be getting the acceleration around 0.33 meter per second square. Now students, this is the magnitude of ape's acceleration, right? Now what do you learn here? You learned mostly about circular motion here. Okay, you learned about circular motion. This question had an idea of circular motion in it, right? Why circular motion? Because you were dealing with what? You were dealing with basically a merry-go-round. You were dealing with a merry-go-round. So we had a circular motion involved in this. We had centripetal acceleration involved in this question. Centripetal acceleration involved in this question. We had centripetal force involved in this question. You have seen the formula. And also we had a small concept of relative motion involved in this question. Now, if you feel that I have missed any concept, please put it in the comment box. The comment box is for you to give feedback. Okay, if you feel that I have missed any part of the first question, please put in the comment box, students. I'm willing to see your feedback. Okay, right. Now let's go forward to the other part. All right. The next question says, Lucy stands on the edge of a vertical cliff and throws a stone vertically upwards. The stone leaves her hand with a speed of 15 meter per second. At the instant, her hand was 80 meter above the surface area of the sea. Okay. Air resistance is negligible and the acceleration of the free fall is taken as 10 meter per second. So they're asking here, calculate the maximum height reached by the stone as measured from the point where it was thrown. Okay. Now, maximum height reached by the stone as measured from the point it was thrown. So see, Lucy has thrown the stone upward, right? Lucy has thrown the stone upward. It's going, but you know that it is slowing down. You know that it's slowing down because acceleration to gravity is acting in the opposite direction, downwards. So that's why it is slowing down. You should also know when something is thrown up. When something is thrown up, it will have negative g value. Why? Because it is trying to slow down the object. When something is going down, falling down, it has positive g value. Why? Because it is speeding up the object, right? Now it's thrown up, okay, it's 15 meter per second. Now the initial speed is also given 15 meter per second, it's thrown up. Calculate the maximum height reached by the stone as measured from the point where it was thrown. Now I need to calculate the height for which the stone has gone, the height. Now for this, you see, for me the initial speed is given to me, that is 15 meter per second. Height needs to be calculated. The acceleration also is known, that is minus g. So basically it's given here minus 10 meter per second square. I need to find h. Now students, think about the equations of motion, SWAT equations. Now which SWAT equation can give you the answer? I need the distance. Some people might think equation number 2, but my dear, equation number 2 has time in it. I don't have time with me. Equation number 3. Okay, so I do not have time here with me. So that's the only possibility that I can go to my answer is by equation 3. And equation 3 says that v square minus u square is equal to 2as. Now there is something missing. This u is my initial velocity, v is my final velocity. Now you might think, what is my final velocity? But students, understand, gravity is trying to hold, to slow it down, slow it down, slow it down. At one point it becomes 0. So when the speed becomes 0, it has reached its maximum height. So your v is 0, students. Now put in all the values around here. So it is minus of 15 square equal to 2 into 10, minus of 10, by the way, minus of 10, so it becomes minus, into h, the height is required here. So minus of 15 square is going to be minus 225, isn't it? The square of 15 is 225. Correct me if I'm wrong, students. 15 square is 225, equal to minus 20h. So that would give me h is equal to, minus minus gets cancelled, 20 to 25 by 20. So if you ask me what is 225 by 20, don't mind me, students, I'm very bad at calculation. So I'm doing 225 by 20. That's 11.25, isn't it? 11.25 meter. 11.25 meter. So the stone goes 11.25 meter from the point of her hands. Okay, from her hand. Now determine the time for which the stone reaches the surface of the sea after leaving Lucy's hand. Now they're asking, look what they're asking. They're asking, I'll just erase everything. Now they're asking me, when will it reach back? See, it has gone up and reached the topmost point from Lucy's hand. Now they're asking me, determine the time taken for the stone to reach the surface of the sea now. Now they are asking us the total journey, time taken to come backward and fall here. Now what's the total distance? See, already from here it has traveled 11.25 upward. Now here, from here, it is 80 downwards. Can you see from her hand 11.25 meter upward it has gone, from her hand 18 meter is down. So now the object, the stone that was thrown has to come from the top till here. So the total distance that is traveled by the stone is going to be 80 plus 11.25, and that's going to be 91.25 meter, my dear students. It has to travel 11.91.25 meter. Okay. Now they are asking me time taken for it. Okay. And I know my initial speed, at this point, students, I just now told you it comes to a stop, right? At the topmost point, it comes to a stop. So my initial speed is 0. I have my d value. I have my u value. Okay. I have my d value. I have my u value. And I have my du. Now they are asking me, and of course, acceleration. This time is going to be plus 10. Why? I told you when the object is coming down, you need to apply plus 10 there. Isn't it? You all must be remembering this. You know that when the object is coming down, you need to apply plus 10. Right? So now, when you are putting plus 10 here, what is going to happen? When you are putting plus 10, okay, now the time taken to fall somewhere approximately there. So I would say you will be using which formula right now, which is the perfect formula for this? Any idea? I have distance, I have time. Now this time I have time. Now I have acceleration. So yes, d s is equal to ut plus half at square. S is equal to ut plus half at square. So look here, students, I have my D 91.25 equal ut, u 0, u into t, then this becomes 0. First part becomes 0 plus half 10 into t square. So I need to find my t. I'm trying to find my t. So I multiply it to that side. So when I multiply to that side, I'm going to get some value here, right? So let me multiply 2. So I'll be getting somewhere approximately 182.5 is equal to 10 t square, right? So now t square is equal to 18.25 now, because 10 is gone there, right? 18.25. 18.25 t square is equal to 18.25. Now they're asking me what is the t value. Okay, now they would ask me what is the t value, the time value to come from here, this point, to this point. Okay, now the time taken here, approximately you will be getting it around 4.3 seconds. 4.3 seconds. Okay, now remember, this is the time taken to come from topmost point to down. It's 4.3 seconds. Well, look at the question. What is the question asked? Determine the time for the stone to reach the surface of the sea after leaving Lucy's hand. Okay. That means I need to calculate the time taken for it to go from here to here also. Okay. So yes, I have everything in my hand. I have 11.25 meter distance traveled, right? So I use the same formula. I have my distance already. 11.25 is equal to ut, okay, plus half 80 squares. So I think this formula might be a little difficult, so I can use the first formula, right? Because I do not want to play with squares. I think v is equal to u plus 80 will do for me, right? Yeah, because I have my v value, I know my u value also. V is 0 and u is already given here, 15 plus 10 into t. So looking at this equation, I find that the acceleration minus 10, sorry, my mistake, acceleration is minus 10 because it is in the opposite direction. Be very careful, students. Even a best of best teachers can do mistake. So why not students? Okay, be very careful. Error mistakes can be done by anyone. Okay, so minus 15 by 10, so you are going to have 1.5 seconds as time. Okay, your time is 1.5 seconds to go upward. So what is the total time for the whole journey, students? 4.3 plus 1.5. So that's going to be 5.8 seconds, students. So the answer for your question that is here is 5.8 seconds. Okay. All right. Now let me tell you something very important. Now, students, you got to know how you do problems based on kinematics. Look here, you have to look for the command terms here. Very important. You must have felt how smoothly the question was done. But let me tell you, there are many ways how you can do a question. And there are many possibilities of getting answers also. IB gives you a flexibility to get your answer. Remember the first question in the merry-go-round, there were two answers. According to marking scheme, there are two answers. Either you can write 2 meter per second or you can write 0 meter per second. For the both of them, they are going to give marks, right? So it gives you more flexibility, but understand that it's you have to do practice. You have to practice enough so that the way how you do questions becomes more smooth for you. And this is not only for IB, this most for most of the international curriculum, and even in CBSE, or if you're doing NEET, practice is the key. But thought process is very important. You have to understand why we do something, why we take a formula, and why should we apply something to it, right? So with this, I will end my today's session, students. We will see in the next video in the next week. Bye, students.